So very good. Assignment number 2, task 2, actually from page 460 in the book. Earlier in this chapter, we encountered some data related to children's injuries while wearing superhero costumes. Children reporting to the emergency center at hospitals had the severity of their injury, variable named injury, assessed on a scale from 0 to no injury to 100, which is death. In addition, a note was taken of which superhero costume they were wearing. The variable's name is hero. Spider-Man, Superman, the Hulk, or Teenage Mutant Ninja Turtles. Use a one-way Anova and multiple comparisons to test the hypotheses that different costumes are associated with more severe injuries. So what we'd like to do is like to open up the data from our text file and simply look for superhero. Double click on that guy, verify that your data looks like what it should be looking like. We have one variable named hero, one injury, exactly as the book indicates. Go ahead and import that. Activate our commander to help us out with the analysis portion of this. And let's go ahead and maximize the size of that. Activate superhero. Click on OK. And the next thing we want to do instinctively is simply to run our one-way ANOVA. We click on means and we see that one-way ANOVA is actually grayed out. Well, nothing's wrong with that. The fact is that our commander does not know that 1, 2, 3, 4, as we had seen in our data set when we imported it, are different categories. As we look at this right here, and I'm actually trying to open this up, we have 1, 2, 3, 4. 1 is actually Hulk, Superman, Spider-Man, and the Teenage Mutant Ninja Turtles is number 4. But R right now is interpreting these as a continuous variable, continuous numerical variable in a ratio or ordinal scale. So level of measurement. So what we need to do is we need to tell our commander that we want to convert these numeric variables into a categorical variables. So we're going to supply the names and we're going to call this uh, hero coded and simply click on OK. And now we have the 4 levels that appear. The first one is Hulk. Second one is Superman. Next one is Spider-Man. And number 4 is going to be Teenage Mutant Ninja Turtles. Click on OK. And now you have categories. If you view the data one more time by clicking on View Data, now you see that instead of 1, 2, and 3, and 4, you actually do still have the 1, but all the 1s are Hulk, all the 2s are Superman, all the 3s are Spider-Man, and all the 4s are Teenage Mutant Ninja Turtle. The question is, are the severity of injuries different by costume that a child is wearing? First thing I like to do is I always want to check for assumptions of normality, because that is one thing that we're required to do when running an analysis. We want to make sure that we're checking the assumptions. The first thing that one of the first assumptions that you always want to check is whether the data from each one of the groups is independent from each other, and we don't know that, so we assume that that is actually the case. Independent means that there's not a child that's dressed up as Superman and also Spider-Man. Um, if you were doing research in a classroom, you want to make sure that data is independent from each other, that students in one classroom are not also in the next classroom, which you are testing with the same test. That's just a very quick, silly example. One thing that you do, which is a very nice graphical um, representation of the data, is to click hero coded by injury. So now we have groups and we can see the standard errors. We can see confidence intervals if we wanted to, or standard deviations. In this case, let's just go with the default setting of standard errors. Click on that and go over to RStudio. And now you can see that we have a mean, which is the large dot in the middle, and we have the standard errors, which are the bars outside of that. And by eyeballing this, we can almost say that, between Teenage Mutant Ninja Turtles, there's a good chance there's going to be a statistically significant difference in terms of severity of injuries. Same thing could be the case for Superman and Spider-Man, where Spider-Man is a little bit lower than this. Hulk and Superman appear to be different, eyeballing it, but may not necessarily be different or entirely different. So statistically different. So let's go ahead and run the analyses. By going back to our commander, I'm going to do one more thing before I run the analyses, which is to check on the variances. And we want to make sure that we have homogeneity of variance. And we have multiple groups here. Bartlett's test is probably the most appropriate for multiple groups. Click on OK, and we want to see that our p-value is not significant, suggesting that the difference between the variance of each one of these groups, Superman, Hulk, Spider-Man, and Teenage Mutant Ninja Turtles, is actually similar to each other. And when we see that the p-value is larger than 0.05, then we can assume that these guys have variances that are similar to each other. So I get back to our commander, and I click on statistics, and this is a means comparison test, so I'm going to click on one-way Anova. And I'm actually going to name this model Hero 1, and it's the first model that I'm running. And my outcome or response variable is injury. The grouping variable is hero coded, and I'd like to see a pairwise comparison, so I'm going to go ahead and click on pairwise comparison. And Tukey's pairwise comparison is what our commander is using to look at differences. So now I'm going to go back to examine my output, and I can see that starting from the bottom to the top, I have the comparisons. Taking it all the way to the top, I have let me see, this is where we start right here. This is where we start. We start with, and I'm sorry, because I had run this analysis earlier, and I'm afraid that I'm overlapping with my previous analyses. So let me see. Hero coded data superheroes. So yes, here we go. So this right here was our Bartlett's test of for variance, checking on the variance. So we can look at this now. So the first thing we're going to do is we're going to look at the model, see if this is a significant model. Hero coded is a significant model. We see that the p-value is smaller than 0.05. The 3 asterisk suggests this is smaller than 0.001. So significant indeed. Our F ratio is 8.317. And here are degrees of freedom for the group, and the sum of the squares and the mean sum of the squares. The next thing that we can see is we can see that there's a mean for each one of these. On the right-hand side, these means appear to be displayed in terms of differences for Superman and Hulk, Spider-Man and Hulk, Teenage Mutant Ninja Turtle and Hulk, and so forth. And you can already see that, hey, listen, these guys are outside of the mean, and there's a good chance that these differences are statistically significant in terms of severity of injury. So we look at Superman at 60. We look at 60. Superman is actually the one with the highest severity of injury. Spider-Man, not so high. And of course, Teenage Mutant Ninja Turtles, the least severe. Next thing I'm going to look at here is I'm going to look at those comparisons or contrast, and Tukey's contrast suggests that yes, indeed, Spider-Man and Superman are statistically significant, and Superman and Teenage Mutant Ninja Turtles are statistically significantly different. So this right here is confirmed with our graph on the right-hand side, and with our suspicion from running our means plot a little bit earlier. The last thing I'm going to do is I'm going to scroll down over here, and we can actually look at some estimates, difference between each one of these, and that's interesting. It's informative. But we do not have something that we usually have and we usually ask for. You know, when we did the t-test, we said, so what is the level or the measurement of effect size? Effect size paired with statistically significant findings or a statistically significant model gives us a better picture. And so in this case, what we want to do is simply code in our, I think we had called this Hero 1. So we code in our model, we ask for a summary, and notice that that is a linear model summary. So by clicking on enter, we can now see pretty much what a regression analysis is, and we had said that regression and ANOVAs are or use the same principle. It's based on the F statistic, F ratio. But now by running the summary, we can see that we have an R squared value of 0.48, suggesting that 48% of the variance is accounted for by these four groups, and that is actually, according to the R squared conventions, a moderate or medium effect size. So along with a significant model, we have a medium effect size, and that's going to be all for this presentation.